Morning, everyone. Welcome to the session 4 of this year's Rubin Data Academy. This session is for catalog queries with tab service. And my name is Yumi Choi. I am a member of community science team. Oh, all right. So this year's Rubin Academy schedule. Um, So this year, again, we focused on the beginner level use of the Rubin Science platform and access to the DP1 data products. And the goal is to help get the new users ready to do science with the Rubin data. But we also have two extra sessions this year, session 11 and 12, providing overviews of upcoming data preview 2, DP2, and the prompt products data set. And this week we have 12 sessions in total, and they are repeated in morning and evening for global audience for maximum accessibilities. But also here in the the Academy website, the slides and the recordings will be available. Right. Before diving into the tech queries, let's go through a few reminders. So the community forum is the place to go if you have any questions or problems working on the Rubin data and any services and tools available at the Rubin Science platform. So in the support category here, um, please make a new topic. But when you start making a new topic, you will see a similar or relevant previous topics will popping up in the bottom of the page. So that way you can also look at if any other users have similar problems or questions as yours in the previous, and they already have a solution to it. If not, then make a new topic with a descriptive titles and some details about your problem. Maybe the error message is useful for us to reproduce your problems and things like that. And community science team is monitoring this support category. So, to make sure all the questions are answered, but other Rubin STEM members or the experienced community members could provide answers to you as well. All right, the dp1lsst.io is the place where you can find all the DP1 related documentations. And there is also the DP1 paper, published paper. So you can cite DP1 papers in your work, or the individual data sets have their own DOIs to cite. So there is the DOIs available for you to cite Rubin's DP1 and data products. And any like general informations about like events and things like that are available at the Rubin observatories, looking at the for scientists sections for the upcoming events and announcements and news and tutorials and documentations. All right, Rubin data policy. So Rubin data right holders are the US or Chilean institute-based scientists and the students, of course, and also the named members of the international in-kind contribution teams. And only data right holders can access to proprietary data and the Rubin science platform. And you can find the list of international data right holders in this spreadsheet. And what do we mean by proprietary? So they are like all the data release, data products, images, catalogs, and the prompt processed images for first 2 years, and also the access to the Rubin Science platform. And what about the public data? All alert packets and prompt catalogs and all the other data after 2 years after their release, and all the documentations and support resources are public to anyone. Okay, any questions? If not, this is today's agenda for this session. So we go through key concepts and the ADQL basic compositions first, and then we'll run through some of the notebook tutorials regarding the catalog queries with the tab service, which is 1 or 2 series. And then some of the portal aspects that are equivalent that I describe in the notebook tutorials. All right. So key concept. TAP stands for Table Access Protocol, and ADQL stands for Astronomy Query Data Language. So maybe let me explain these concepts using a simple restaurant analogy. So let's say there is a restaurant and you want to get some food, but you don't just walk into the restaurant and go to the kitchen and pantry and dig up what they have and then have their food, right? It's not the way, but you go there and then look at the menus and to figure out what they serve and what do you need, and you come up with what kind of specific food you want and place an order to your server, and server takes your order and pass that to kitchen, and then kitchen cooks your dishes, and then server will bring you the food you ordered, right? So you can think like database is the kitchen and the pantry, and the tab schema is the menu. So showing you how the database, the restaurant is structured. And the under menu, in the menu, you have multiple categories like the appetizers, main courses, dessert. So that's showing what kind of tables in a schema is available. And under each category, you have items like specific dishes, right, with descriptions of detailed ingredients and the way of cooking, things like that. So those are uh, corresponding to the columns inside a table. So after you look at the menus, you figure out what kind of food you want and write down, your orders with specific request. So in ADQL is a standard language for you to write your order to submit to the tab service. Oh, here the tab service is like your server who's taking your order and communicate with kitchen and then bring the food you order to you. So the tab service is really this, the standardized way to access and allow the user to do like server-side filtering, joining, and the cross-matching. And it's really scalable for big data, so have many advantages for large surveys. And also, it provides a reproducible workflows for by for example, if you share your queries with your colleagues or present it in your paper, then people can use the same exact queries to do their own queries and get the exact same result as you do. And then many of the tab functionalities work both in portal and the notebook aspect, which is great. And the ADQL, if you're not super familiar, but if you're familiar with the SQL, that's pretty similar to SQL. And ADQL is standard across the virtual observatory services. So this is not just for the Rubin service, but all the other virtual observatories, you can use the ADQL. All right, so I think I covered the tab schema and query, but this is the like basic formats of an ADQL query statement. So usually it has at least minimum these three components at the minimum, like select what kind of columns from what kind of catalogs or tables, where which provides the constraints you want to apply to this query. So this is a generic example, like select column 3, 4, 5 from my survey data table, where the column 1 is greater than 1, greater than 0.5, and column 5 greater than less than 10. Okay, so in this session, I'm gonna just use many different tables, but not providing detailed descriptions of each tables. But there are the sessions for the data products. So these sessions 7, 8, 9, 10 will be taking place tomorrow and Thursday, I think. So if you want to learn details about the DP1 data products, please join those sessions. All right, so now we're gonna jump into the notebook tutorials, but does anyone have any questions about the concept of TAP and ADQL? If not, let me share my, oh, did it go in here? Okay, so RSP, I think the previous sessions covered the RSP. So we go to data.lsst.cloud and I just log in and click the notebook aspect. Oh, there is a question in the chat. Let me start my server first. What is the option add remaining a retrieved column? So I think if you're asking about the as inside your query, and I'm gonna show that example in a couple seconds, but I don't understand. Oh, renaming. Yeah, it's possible. Yeah, I'm gonna show it to you as well. Good question. All right. So under the tutorial tabs, go to DP1 and in 100 level, 102 series is the series we're gonna go through today. Okay, so this one in the introduction, it briefly talk about the tab uh, and some of the tab glossary, and we'll get back to this best practices for tab queries at the end of this notebook. So I think I covered most of this glossary. So tab schema is basically your menu and shows what kind of table collections in each schema. And each table has a lot of columns. And query is your specific orders written in ADQL language. And the result is the output of the tab service. Okay, so this is the basic query statement we just talked about. So to run through, we import the packages we're going to use in this notebook and then instantiate the tab service. So this way your waiter or server is ready for you. And so first thing is look at the menu, right? So explore the schema is our first step. So we need to figure out what's available in the Rubin tab. And in this case, exploring the tab schema, we are going to use synchronous queries, which is typically not recommended. But this is only good for when your query is really quick and your workflow is required to like sequential execution. Other than that, we always recommend to use asynchronous queries, which is not blocking other, cell executions. Hmm. Right. So what we're gonna do is select everything from tab schemas to look at what kind of menus available in this service. So there are four different schemas available in RSP, the Rubin tab, and the schema we're interested in is DP1 schema. And then this is just fetching the result from the query, but you can also convert your result to a AstroPy table, which might be more familiar format you could play with. And then now we know we want to look at the DP1 schema, and we want to figure out what kind of tables are available in the DP1 schema. So this return the 12 list of 12 tables in the DP1 schema. So there are object table, source table, for source table, blah, 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 and also provide the descriptions for each table. So you figure out which table you want to use. And then the next step is to figure out what kind of columns in a table are available, right? So let's look at the dp1.object table and retrieve all the column names, and the column data types and descriptions and units. So we can display the result. All right. So it says in the object table, there are 1296 columns. It's a lot of columns. You definitely don't want to retrieve all the columns in the object table, of course. So you have to figure out which columns are needed for your science, right? So this is one good way to explore what kind of columns available in each table and what you need for your science. Because there's a lot of columns in this object table. You can search for like just list all the columns that includes coordinate in the column names, and there are RA-DEC and RA-DEC errors and their covariance columns. Okay, and then you can also print the object table's data type, unique data types. Right. This section now shows the best practices for tab queries. As I mentioned at the beginning, except for like few special cases, we always recommend to use asynchronous queries, which allows you run your query as a background job on the server side, and then you can do other cell executions while the query is running. And then you can retrieve the query results later when you are ready. So the workflow is you write your query first and then submit that as a job, and then run the job and check the job phases. It's not necessary, but it's really useful. And then if your job is encountered an error, then display the error message. So figure out what's the problem with your submitted query. And then once the job phase is completed, then you can fetch the result as a result. And while if your job is running more than a couple of minutes, then you work on other things, and then check the status of your job. uh, there's a one way is to look at the job monitor. So in the notebook aspect, if you click this plus button, then there is a Firefly tab. So you click this one and it will launch the Firefly viewer. And there is a job monitor tab, and then you click it and it should list the most recent jobs you just run in the server side. I think the job submitted from the notebook aspect takes a little time to show up in the job monitor, but portal submitted ones are uh, presented in a real time, almost in a real time. Anyway, so this is the way you can check the job status. Here we go. So the column has like job title, service ID, and the job type, it's temp service, and when the job started, and when created, and when the job started, and when it ends, and what is the phase. And the control tab shows the displaying your result uh, or information about the job, and you can also delete your jobs. Okay. Um, and then another thing is not to use select stars, which select all the columns in a table. So, for example, as we see, uh, there is over 1,000 columns in the object table. So you don't want to use select all, but specify the columns you want to retrieve first. And also, the the Rubin data is sharded based on their spatial coordinates, and then stored in individual files and stored across many across different servers. So the files are physically located in different servers. So the way to save um, resources and also make your queries much faster is to use the spatial constraints, if it's possible. That means that if you provide the spatial constraints, then it only scans the relevant files, and to execute your queries. If there's no spatial constraints provided, the query, the query service will scan all the files, and which takes a lot of time. Mm. So for the spatial constraints, you can use Cornsert, which has the this statement where under where you provide the constraints, we provide the spatial constraints in this case using the circle. So contains equals 1 when the points are within this circle. So in the points, you pass the column, the spatial sky coordinate column names in your table here. And then in the circle, you provide the central coordinates and then searching radius of your sky region of interest. And then put it in the contains equals 1 statement. So this means that retrieve only the rows if the object coordinates are within the defined circle. And maybe you think we can use RA and DAG between this and this coordinates might work in the same way, but it's not. In the so the tab service doesn't interpret this between statements as same as this Cornsert or the other spatial constraints. So please use Cornsert or polygon search if you need more complicated region to define. Okay, so we can write a query to search for the ECDFS fields and just retrieve the coordinates in this searching circle. Okay, the query is running, taking longer than usual because many of us are doing the same thing, I think. All right, so it returned 141 objects that meets this spatial constraints. And if you want to use the polygon search, then just simply replace the circle part here, circle function, with the polygon function, and just provide a pair of array and deck for corners of your polygons. You can also use column constraints. So in this case, this query is the same as above, but with one extra constraint on C model Met column in G band. So we now want to retrieve coordinates and the C model magnitude in this searching circle, inside this searching circle, only for the object that has the GC model magnitude less than 20 magnitude. Right, so I'm not going to run this query now, but is there any questions before? Oh, maybe we just to summarize the best practice for tab queries. So most cases, please use the asynchronous queries, which makes your queries much faster and saves some resources, and specify what kind of columns to be returned. Do not use select all. And also, when it's possible, use spatial constraints on sky coordinates, which also makes your query much faster and saves some resources. And if needed, you can also add column constraints. Okay, so this is the first tutorial. And then if there's no questions, I can move on to the next one. Okay, so yeah, we covered TAP and ADQL concept. So we import the packages and instantiate the TAP service. And in this notebook tutorial, we show how to manipulate columns. So it's answering the questions came up earlier. So this is the basic queries, right? You just retrieve array and deck from the object table, but you can rename the columns using as statement in your query. So for some reason, if you want to rename the chord underscore array as a array and chord underscore deck as a deck, you can do this in your select inside the select statement. And so that way you can just rename the columns. And here we just yeah, make sure that in the returned result, the column names are array and deck, not the chord underscore array, chord underscore deck. Okay. And also, you can apply ADQL functions inside select statement. So, for example, um, 80 the radians functions convert your coordinates in degree to radians, and the distance function computes the angular separation between the point you identified and the object coordinates, and save that calculated angular distance as a distance column. So you can do that while so we submit the query and it's completed. So in the result table, you can see the array in radians, and declination is in radians, and distance between your source and the center, the position you defined in the query, in degrees. And in the session slides, there is which page? Oh, here. Shows what kind of ADQL functions are available in the RSP tab. So look, please refer this slides later. Um, okay. And then other functions we could use is that Sci-SQL Nanojansky to ABMAC and to ABMAC Sigma. So this converts the flux to ABMAX and ABMAC errors. In many DP1 tables, we provide various fluxes, but only the PSF flux and the CMODEL flux are pre-computed as a magnitude and provided the magnitude columns, but other fluxes like the Cersec flux is only provided in the Nanojansky. So if you prefer to work with magnitude, then inside query, you can convert those fluxes to magnitude and magnitude errors, and then save those as a new column. So this is our query now, and we submit the query. All right. So now the result table has the G Cersec magnitude. Let me scroll a little further. And also G magnitude, Cersec magnitude errors as well. So now you can work with those magnitudes. And then the other thing you can do within the query is derive new columns using the original columns. So for example, the tables have, object tables have same order of magnitude in all six bands, U, G, R, I, Z, Y, but we don't provide the pre-calculated colors. So you can calculate the colors and define them as new columns in your query. So you don't need to calculate colors later. You can just access to those color columns. So now look at the result column names, shows the UG, U minus G color, G minus R color, all the colors you define in your query. Okay, so now we show this sections will show how to constrain column values. The first one is applying relational operators like the equals, less than, greater than, not equals, and things like that, right? So we have the same queries as above, but we added now have three more constraints um, in each magnitude, C model magnitude. So here we want to select all the objects that are brighter than 25th magnitude in all six filters and within this searching circle. So this is our new query. And okay, so job completed. And then you can just print out what is the mean and max colors in all the color combinations you defined in the query. Okay, and then apply operators to functions. So let's say you want to apply the constraints on your Sersic magnitude, um, which is not provided in the object table as a pre-computed columns, right? But we have to convert Sersic flux first to magnitude to use the Sersic magnitude. So you might think, oh, this is we convert this and save this as a G underscore Sersic magnitude column, so I can use this column in the where statement to constrain on magnitude. But this is not working because where statements only takes the original column names in the table. So the way we have to do is use these functions in the operator. So inside the where statement, you have to use this sizeable function to convert flux, Sersic flux to magnitude and apply operation like less than 25th magnitude. So this way you can do select the object that are brighter than 25th magnitude in Sersic magnitude. Okay, so this is the job running, but I don't think we need to get the results. Okay, and you can also use between and statement inside the where. Um, for example, if your values in A column between values in B column and values in C column. And so in this case, the syntax matters the order. So really you have to pay attention what kind of relation you want. But please do not use, again, do not use between statement for the spatial constraints, like RA between 30 and 60 or something like that. The tab doesn't interpret that as a spatial constraint as we do with the cone search or polygon search. So this really with the between um, using between for the coordinates is not good for making an efficient query. Okay, so here we're gonna select the blue object, which has like blue SED slope. So meaning that it's emit more fluxes in blue filter than the red filter. So magnitude in G should be less than R and than I, right? So the constraint we want to apply is R band magnitude is greater than G but less than I. So this way we can select the blue object. And we wrote that query and then retrieve the result. So for this one, you can see object ID GRI magnitude. You can see G magnitude are the smallest, and I is the largest value. All right. And then also there is an in statement you could use inside the constraint. So for example, your colleagues gives you the list of object ID, or you have a table from the published paper that only contains the object ID, then you want to retrieve other columns like magnitude or coordinates, or you want to construct the light curves, whatever. Then what you can do is you construct the list of object ID and then pass that uh, to the where statement. So select object ID coordinates of the object from the object ID where the object ID is in this object ID list you get from somewhere else. Um, so it's running and the job completed. So you can see the object ID is now exactly the same as the ones in the ID list we provided. All right, the section 4 is about the manipulating the result. So you probably want to check whether your query is right or not by submitting job and then see you get what you wanted. So in that case, you probably limit your number of returning rows, right? One way is using the top. So for example, um, you know, do this search and then just return the top 10 rows of the result. So if we submit this query, it's really resulting table length is equal to 10. So it's really returning the top 10 rows. But maybe if your search is large enough, then the top 10 doesn't necessarily mean that your query will also run fast. In that case, if your searching is not really confined in a small sky area, then I recommend not using the top 10 or top 5, but instead try with a really small sky area. So that way you can get the results really fast, right? And then also you can sort the results tables. There are two ways, basically. One, you first retrieve your data and then convert it to the AstroPy table and use the sort method provided by the AstroPy. So this is after query. So you run the job and then just convert the table, convert the result as an AstroPy table, and then sort the table based on the columns you want. Right. So now it sorts by the magnitude, and you can say descending or ascending order. And then the other way is sort the table inside a query by using the order by. So here now it's the same query, but at the end you said order by G magnitude, and I want the descending order. So submit the job and complete. And look at the result. It did the same thing, right? Descending, it stored the table descending order. So there are two ways, and depending on the query uh, heaviness, you might want to take one last step inside your query just to retrieve, and then as a post-processing, you can sort your table using the AstroPy sort method. All right, finally, you can aggregate rows. So in this case, for example, like if you want to figure out how many R bands visits has been taken in the ECDFS field. So just count the midpoint MJD exposure time, and that records basically how many visits happened. So uh, count that and then save that as n visit columns, and also figure out what is the mean and max exposure time taken for the R-band visits inside that field. So this is the query, and you submit the job. And then display the result. So in the ECDF fields, there were 237 R-band visits, and the minimum MJD for the visits were this, and the maximum was this. And finally, you can have apply the aggregate functions to groups of rows instead of the full data. So for example, in this case, if you want to figure out how many sources were detected um, in the visits, R-band visits, between these 3 minute windows by setting the MJT range. And I want to group by the visit number. So per visit, how many sources were detected in R band? So we're just counting the number of source ID and then save them as n sources. But this source ID will be grouped by the visit number. Right? So job is running. While waiting, is there any questions posted in the chat or
Haven't seen any new ones in the chat yet.
okay? Maybe I will open the next tutorial we'll work on. You okay? That's done. Now, so in this field, there are within that 30 window time window, 30-minute window, there are 8 different visits, and then um, per visit there has been 20, 27K each source were detected in R band. So that kind of statistics you can do inside your query. All right, let's move on to the final notebook tutorial, which is to describe the cross-match to uploaded table. So I'm gonna just quickly go through this one because we are running out of time. So we first import all the packages we are gonna use. And so maybe I don't shouldn't run the query, but so this is just as an example, we stored an example user table. This is the Sloan Digital Sky data uh, table, and we store it. So the query now you write is that, user table one, UT1 here, has RA and DEC information. So in the worst constraints, you are cross-matching your user table, your table against the object table, DP1 object table. And by comparing their coordinates are in RA and DEC and with a matching radius of 1 arcsecond. And so you wrote the query, but then when you submit the query, you have to add this parameter. So upload means that your upload table name in the tab server, and then UT1 is your table read. So you just upload your user table to the tab server, and then the cross matching against the object table in the server side. So this is one way. And also we can apply the column constraints for this case, right? You can apply the magnitude constraints or the difference between the Sloan R band and then DP1 R band magnitude less than 0.1 meg. So to make sure select not just they are spatially close, but they are physically also the same object. And another way is that using the identifier. So the previous example shows the spatial cross-matching, right? But if you have like common identifier between your table and the DP1 table, then you can use those identifier to join. So in this example, we use the Gaia Gaia tab. So from the RSP, you can access to the Gaia database by setting the Gaia tab service and then retrieve some data for the main belt asteroids. And then here the MPC designation is the key to join against the DP1. So we have in DP1 we have MPC org table that has the columns about the orbits of those asteroids. So you can use the MPC org table, using the MPC designation to join these two tables. Right. And then I think we briefly just go to the portal aspect and do some of the quick queries. Okay, so things like that. So in Portal, click the DP1 catalogs, and there is a lot of the same four schemas we saw in the notebook tutorial, but we are interested in DP1 schema, and under DP1 schema there are 12 tables are available, and we select the object table here, and on the left columns you can enter constraints like the spatial constraints. You can do cone search or polygon search. And you can also apply temporal constraints and object ID constraints. But if you select and you have to specify which columns you want to retrieve, right? So let's say we want to do cone search about this coordinates, and then we want to retrieve these these columns, and then you can just click the search button or populate the an ADQL. So if you're not super familiar with the ADQL, you can start with the portal and just click and then type, whatever constraints you want to apply, then it will write ADQL for you. So this is easy way to learn how to use ADQL. And if you want to apply like constraints on columns, maybe you can like maybe. So there is a running value columns from the Schlagle dust map. So if you want to apply this column constraints and then populate the ADQR, then you can see this line is added. So in this way, you can submit a search, then it will return the result for you. And you can also do like table joins in Portal 2. What just happened? All right, so now you can just clear your ADQL and paste the query we just copied and submit the query, and it will run for you. And you can send the job to background and go back to the catalog. And you can also see the upload table functionality here. So you can upload your user table and use that in your queries as we described in the notebook tutorial. And this is the 3 table join examples. Maybe we can skip. All right, I think that's all I wanted to show today. Oh, oops. All right, so these are the list of tutorials that we briefly go through today. And Lastly, there is an exit survey for this particular session. It's only 4 tables, 4 questions, so it's super easy. Please do the survey, and we'll use the feedback to improve sessions for next year. Okay, there's a question. Could you explain again the difference between cone search and polygon search? Oh, cone is just defined center position and then searching radius. It's just cone because at farther distances, you are looking at the larger physical scale. So your searching shape, it's basically cone shape. But if that's why we call cone search. But polygon search is if you need to define more complicated shape of your searching region, then you can use polygon and then identify the corners of polygons. Um, does that your does it answer your question, Ruba? Think so. Okay. Okay. Uh, yeah, so is there any other questions about the catalog queries with tab? If not, we can take 2 minute break and see you all in the next session. Thank you for coming.